Y'all, so tired, but we're gonna keep going today. So I remember last time we were looking at this example, and LU decomposition. All right, so let's type up these problems in here. So we're doing the first example, so this one, and then okay, so we have first row is 111, 101, 252. Was it 01252, and B is 217. Okay, so if we go here, A equals np dot array. One one one, no, 202 434. P equals np dot array. Oh wait, I'm copying the wrong thing. Two 217. Okay. X equals LA dot solve B print X. Matrix is singular. Well, let's see. Yeah. Scipy.linalg singular matrices. Singular matrix is one that is not invertible. This means that this is really weird. What if we try LST as Q? Die. It's least squares. So if we go back to the first thing here. Yeah, I don't know what this is saying. Okay, won't run matrix is singular. Okay, that's gonna be it for this example, but why don't we try this? Example 2, 1, -1, 1, -2, 1, 1, 1, -1, 2, 3, 1, 1, -1, 2, 1, and b is given by 1, -1, 2, 1. Run this, we get the solution for 300. Awesome. Okay, I'm assuming if we do example 3, we'll get something similar to example 1. Yeah, I think now we get to a little bit of the protein. So, okay, I think we have to take notes because I've never heard of LU decomposition before. A lower triangle matrix is a matrix with 0 above the diagonal. For example, okay, a unit lower triangle matrix is a square matrix with 1s on the diagonal and 0s above the diagonal. Wait, a lower triangle matrix is a matrix with 0s above the diagonal. Oh, so the empty spot. Upper triangle matrix is a matrix with 0s below the diagonal. A unit upper triangle, okay. Theorem. Let E be the m by n matrix with 1s along the diagonal. C in the entry at row I and column J with I bigger than J. And all other rows are 0s, or entries are 0s. Then for any m by n matrix A, matrix multiplication EA applies A to A. Yeah, okay. Then for any m by n matrix A, matrix multiplication EA applies to A. The elementary row operation, add C times row J to row I. Oh, so I see. That's why I think it's using a E as like elementary row operation. So this matrix is basically like a formal way to define adding a constant times a row to another row. All right. Yeah, I'm gonna just screenshot this one because I am not typing out these matrices. Do this. Nice. Sweet theorem. I don't understand pages, bro. Oh, can I? Okay, not left align objects. Bruh. I'm a genius. Alright, consider the matrix A equals 1 negative. I already did. I feel like I was like, there's no way 25 minutes passed. Oh, there we go. There it is. The elementary matrix which adds negative 1 times row 1 to row 4. Okay, so we're gonna do all this in Python in the class, I hope, because I'm not trying to do this by hand. Then A has an LU decomposition. I keep thinking LU is supposed to stand for something, but it doesn't. Lower upper or it does. Oh. So unit lower triangular matrix means that we have numbers below, but it's all zeros above. Sick. Okay, we're gonna try to do the examples after. Just want to get through this reading though. Example, compute the LU decomposition of this matrix A, add negative. So, oh, so this is making the upper triangular matrix. Wait, I don't get this. I want to see how this. Damn. So we're getting zeros here. Add row 2 to row 3 to get a 0 here. So we did 1, 2, 3 elementary row operations. I don't understand these subscripts. E3231, E21. Row 1 to row 2, row 1 to row 3, then row 2 to row 3. So we have just shown. Okay, so this is A. So we did, if we look at to the leftmost matrix, 1, 0, 0, negative 1, 1, 0, 0, 0, 1. We want to add negative times negative 1 times row 1 to row 2. Okay, so we're multiplying row 1 by row 2 times negative time. We're adding to row 2 the negative of row 1. That's what this matrix is saying. Then we're adding negative 2 times row 1 to row 3. So whichever row we're giving or attributing the operation to, or dedicating the operation to, that row will contain the coefficient, and then the 1 sticks to whichever row is like you're adding to the main row. And then we adding row 2 to row 3. So that's gonna look like add row 2 to row 3. but I don't know why does the matrix look like this? Add row 2 to row 3. Let's look at the first row operation. Add -1 times row 1 to row 2. Then -2 times row 1 to row 3. Oh, I see. So if column 1 is like row 1 stuff, row 2 stuff, if you're adding stuff from row 2 to row 3, then you would go to the column 2. So this here is like, okay, it's in the second column. There's a 1 here. So we're adding the 1 times row 2 to row 3. That's how. Okay, so we rearrange the equation to get A equals. So we inverse it all. So okay, so bring left to right over, left to right, left 3, 1. Okay. Then 2, okay, so then A is equal to all these matrices. Oh, so we multiply A times the row operations to get a U. Then we multiply that U by the. These are inverses, I'm assuming, of the row operation matrices. Then we multiply these together, and we get A is equal to E times U. Therefore, A is equal to LU, where L, okay. Okay, I think I'm starting to understand this now. Seems like, okay, yeah. Okay, let's look at another example. So we compute the LU decomposition of this matrix here. So people, okay. I'm sorry for the short videos, guys. Just I have so much going on every day, even during summer break. But I'm trying to squeeze at least one video in. And I'm glad I am, because just even 25 to 30 minutes every day is making me a bit better and better. Yeah. So we compute the LU decomposition of this matrix. So, oh, so we want the lower, this is lower, right? Lower, upper. So we want, oh, okay, we want to create an upper matrix. That means you have to make a lower first. Yeah. All right, you know what? Let's just keep going for a bit longer. Get this example through it. Theorem, suppose A has an LU decomposition, A equals LU, then the rank A is equal to the rank of U, and the determinant of A, oh my god, this is embarrassing. Okay, it's just okay. Okay. I think I'm gonna call it for today then.